So there are two types of chemical reactions, either exergonic or endergonic. So the exergonic reactions are spontaneous because they increase the entropy, so they follow the second law, and they have a net release in energy. While endergonic reactions are not spontaneous, so they require a net input in energy. So why is it important that I underline the word net? Is that just because it's releasing energy doesn't mean energy is only coming out. There was also energy that went in. So and for the input, there's also some energy that was released. It just means that the energy that was absorbed was greater than the energy that was released. So how we compare these things is with a Gibbs free energy difference, symbol over here. Now this little naught or standard sign just means that it was when the reactants were at a concentration of 1 molar and a pH of 7. So how we get this is we do the energy or the Gibbs free energy of the products minus that of the reactants. So if we have our graphs over here, we had high energy reactants and then low energy products, which means that there's a small G products and a big G reactants, so which gives us a negative delta G. So for exergonic reactions, negative delta G, which means entropy increases. In endergonic reactions, if we look at our energy graph over here, we have the reactants have low energy, but then the products have a high energy, which means that energy went into the reaction and then they gained energy in total. So the energy of the products is a big GP minus a small G reactants gives us a positive delta G for endergonic reactions. So if we look at biological examples of these reactions, we have here glucose, a 6-carbon molecule, being broken down. And breaking those bonds requires an initial investment of energy, but the energy released is greater, so there's a net release of energy by breaking those bonds, and then you end up with the carbons, become carbon dioxide and whatever, then you have the energy in the form of ATP. However, in endergonic reactions, you're going to require energy. So here we have a bunch of different amino acids, and we're going to need some energy to be able to combine them and make a chain of like a polypeptide. So over here we have an example of an exergonic reaction. We have sucrose, and then put in water, and we get glucose and fructose. So we broke it up into glucose and fructose, and we released energy, net release of energy. So this is an exergonic reaction, negative delta G of, in this case, negative 5.5 kilocalories per mole. So this is exergonic, it follows entropy, and therefore it is a favorable reaction. It will occur spontaneously. But what if we wanted to do the opposite? What if we want to take glucose and fructose and join them together to make sucrose? How would we do that? Well, first of all, recognize that this is an endergonic reaction, which means it's not going to happen spontaneously because it's not more entropic, but we need an initial input of energy. So how are we going to do that? How are we going to take this unfavorable reaction and turn it into a favorable one? Well, we're going to do something called coupled reactions. So we're going to take a highly exergonic reaction. By highly, I just mean it has to be more exergonic than this one is endergonic. It'll make more sense when we use actual numbers. So if we take ATP and break it down into ADP and another phosphate by itself, we release 7.3 kilocalories per mole. So here we have a negative delta G, right? But if we wanted, and then also if we wanted to just take the glucose and the fructose to make sucrose, that has a positive delta G, because it's endergonic, of 5.5 kilocalories per mole. So if you add up the 5.5 with the negative 7.3, this negative one is bigger than the positive, so it'll work out to give us a total delta G of negative 1.8 kilocalories per mole. So since this is overall negative, so it's overall an exergonic coupled reaction, it will occur. So how it actually happens is here we have our glucose and our ATP, and then after that it'll make ADP and glucose 1-phosphate. The glucose 1-phosphate will now combine with the fructose, and that will make our sucrose over here, and then the phosphate. So I forgot to draw the line over here. Yeah, so overall, this is a favorable reaction, so it will occur, although it wasn't spontaneous alone, the formation of sucrose alone. is endergonic, so it's not spontaneous, but when we do coupled reactions, we get an overall exergonic reaction, which is favorable and will occur. To get the total delta G of the coupled reaction, simply add up the two individual delta G's of the reactions that you were coupling together.